You're on an airplane when you feel a sudden jolt. Outside your window, nothing seems to be happening, yet the plane continues to rattle you and your fellow passengers as it passes through turbulent air in the atmosphere. Although it may not comfort you to hear it, this phenomenon is one of the prevailing mysteries of physics. After more than a century of studying turbulence, we've only come up with a few answers for how it works and affects the world around us. And yet, turbulence is ubiquitous, springing up in virtually any system that has moving fluids. That includes the airflow in your respiratory tract, the blood moving through your arteries, and the coffee in your cup as you stir it. Clouds are governed by turbulence, as are waves crashing along the shore, and the gusts of plasma in our sun. Understanding precisely how this phenomenon works would have a bearing on so many aspects of our lives. Here's what we do know. Liquids and gases usually have two types of motion: a laminar flow, which is stable and smooth, and a turbulent flow, which is composed of seemingly unorganized swirls. Imagine an incense stick. The laminar flow of unruffled smoke at the base is steady and easy to predict. Closer to the top, however, the smoke accelerates, becomes unstable, and the pattern of movement changes to something chaotic. That's turbulence in action, and turbulent flows have certain characteristics in common. Firstly, turbulence is always chaotic. That's different from being random. Rather, this means that turbulence is very sensitive to disruptions. A little nudge one way or the other will eventually turn into completely different results. That makes it nearly impossible to predict what will happen, even with a lot of information about the current state of a system. Another important characteristic of turbulence is the different scales of motion that these flows display. Turbulent flows have many differently sized whirls called eddies, which are like vortices of different sizes and shapes. All those differently sized eddies interact with each other, breaking up to become smaller and smaller until all that movement is transformed into heat in a process called the energy cascade. So that's how we recognize turbulence. But why does it happen? In every flowing liquid or gas, there are two opposing forces: inertia and viscosity. Inertia is the tendency of fluids to keep moving, which causes instability. Viscosity works against disruption, making the flow laminar instead. In thick fluids such as honey, viscosity almost always wins. Less viscous substances like water or air are more prone to inertia, which creates instabilities that develop into turbulence. We measure where a flow falls on that spectrum with something called the Reynolds number, which is the ratio between a flow's inertia and its viscosity. The higher the Reynolds number, the more likely it is that turbulence will occur. Honey being poured into a cup, for example, has a Reynolds number of about 1. The same setup with water has a Reynolds number that's closer to 10,000. The Reynolds number is useful for understanding simple scenarios, but it's ineffective in many situations. For example, the motion of the atmosphere is significantly influenced by factors including gravity and the Earth's rotation. Or take relatively simple things like the drag on buildings and cars. We can model those thanks to many experiments and empirical evidence. But physicists want to be able to predict them through physical laws and equations, as well as we can model the orbits of planets or electromagnetic fields. Most scientists think that getting there will rely on statistics and increased computing power. Extremely high-speed computer simulations of turbulent flows could help us identify patterns that could lead to a theory that organizes and unifies predictions across different situations. Other scientists think that the phenomenon is so complex that such a full-fledged theory isn't ever going to be possible. Hopefully, we'll reach a breakthrough, because a true understanding of turbulence could have huge positive impacts. That would include more efficient wind farms, the ability to better prepare for catastrophic weather events, or even the power to manipulate hurricanes away. And, of course, smoother rides for millions of airline passengers.